How was everybody's weekend? Hopefully super exciting. Um, all right, well let's get to it then. So last time we talked about U-substitutions, and we're going to continue with that today. Um, work a bunch more examples, and then hopefully that'll start to kind of sink in. So let me just start here with a clean sheet. And let's just sort of remind ourselves what the idea is. Actually, let's go back to before. So the idea is you want to find a part of the integral whose derivative is elsewhere in the integral. Um, and so let's start with sort of a good example of this. Um, the integral of tangent of x dx. Um, So if we look at this, we say, all right, there's really only one term here. So we're kind of stuck at first. But how else could we write tangent? How else could we write tangent of x? You guys need to get some coffee. No, Willie, Mr. Young. Oh, we got a whole whopping three of you here today. That's great. All right, well, fine. You guys need to learn how to drink some coffee. Um, we can write it as sine x over cosine x. Um, and now is where we can pull a substitution trick. Um, Now we've really got two options here. We could let u equal sine x or u equal cosine x. And for reasons that hopefully will become clear in a minute, let's try u equals cosine x. Um, if that's the case, what's the derivative of cosine? Derivative of cosine. Yep, minus sine. Okay, so the differential is minus sine x dx. Okay. All right, so then what I'm going to do is I'm going to solve this for dx in terms of du. And in this case, all I have to do is divide by minus sine. Okay, once I have that, then I can take this and this and then go back to my original integral. And then we said that the cosine in the bottom we were going to call u. And then dx we just found was du over minus sine x. And so the signs actually cancel here. Um, the minus sign doesn't, of course, which because it's a constant, I can just pop it out front. And so now we have something that is just du over u. All right, so what's the antiderivative of 1 over u? This is one you guys probably are going to forget. All right, and Dr. Dunaway with the clutch. Um, Yeah, so it's the natural log of the absolute value of u, and then of course our plus c. Um, and the natural log, sorry, the absolute value, like some people are super picky about it, some people aren't. I kind of am because it's wrong otherwise, but yeah. So just don't forget the absolute values. All right, so once we've got that, we can replace u with what we had, which was cosine of x. Um, Mia, shh. There's somebody outside, and this is just unacceptable to her. Okay, so we could leave it like that. That's perfectly good. But sometimes you'll see this written in the following form. And the reason that these two are equivalent is, of course, because coefficient out front of a logarithm can become an exponent on the inside of the logarithm. And if it's a minus 1 that's out front, then we could raise cosine x to the negative 1, and that just means 1 over cosine, aka secant. So sometimes you'll see it written that way. Um, yeah. And actually, Dr. Dunaway's point here is worth mentioning. So, depending on the context you're in, if you see log for log, um, it might, depending on the subject that you're looking at, just mean the natural log. So, for example, in Mathematica, um, the natural log is just written log, and if you want to do a different base, you have to change the syntax up. Um, in theoretical computer science, often log means log base 2 because, of course, everything's in binary, and that's why it's base 2. Um, but in other situations, the log is log base 10. So typically in astronomy, for example, all the logarithms are done base 10. In any time really that you're using calculus is when we do everything log base e or natural log. Um, which of course means econ, most math subjects, etc. Um, so you just have to be kind of clear as to what base logarithm you're working with. But I'll just go ahead and stick with writing L in for log. Um, Natural log here just because that's what you guys are used to. So, okay. So the trick here, right, was to recognize that part of the integral, part of the thing that we were dealing with, um, involved the derivative of the rest of it. And what will happen is if you get to these two steps here, if you get to those two steps and not everything involving x disappears, okay? So like for example here, let's say that we were unable to cancel that sine x out and we were left with things in terms of both x and u, then we would have been kind of in trouble, and that usually, not always, but usually is a sign that you've incorrectly picked u or incorrectly taken its differential. Um, so if that happens, then just check your work, try a different u, etc. Um, and it's worth bearing in mind that um, this is probably unlike taking derivatives, which there were rules and you just did it. Um, U-substitutions or doing integrals in general are a bit more of an art form and require a little bit more finesse. Um, and the next example will actually demonstrate that kind of in spades. Um, if we can integrate tangent, well, let's look at the integral of secant. So in this case, if we tried the same thing as what we did a minute ago, we'd have this. And that's not really going to help us at all because we don't have the derivative of cosine anywhere. Okay, so the previous sort of approach is not going to cut it. Um, so what we're going to do instead is kind of evil. It's one of those things that once you see it, you'll never forget it, but you would have, I mean, you guys probably could have eventually come up with it if I locked you in a room or something and said you can't leave until you figure it out, which I guess is a little bit too much like being in quarantine because of a coronavirus, but whatever. So what I'm going to do is I'm going to multiply by a very cleverly chosen thing. And again, you might think, where on earth did this come from? Um, and is this valid? Okay, so first off, is it valid? Yes, because really all I've done is multiply by 1, right? The thing in the fraction that I've got there has the same thing in the numerator and the denominator, and so if I multiply by 1, well, that doesn't change what I have. Um, Okay, so that's okay. Now, why would I have chosen that? Well, because it works, and we'll see why it works here in a moment. So I'm going to go ahead and multiply this out in the numerator. And so I get this. Okay, so the secant that I had originally, I can distribute to the two terms in the numerator, and so I have secant squared x for the first term, secant x tangent x for the second term, and then the denominator is secant x plus tangent x. Okay, so at this point, then I want to try some sort of substitution if I can, and so let's see what we've got. Well, let's try this. Well, what's the derivative of secant? So derivative of secant x. Yep, secant tangent. Okay, good. So that's the first term. And what about the derivative of tangent? Okay, so the second term is tangent, so what's its derivative? Yep, secant squared. Good. Okay. All right, and then all of that is dx because we're working with a differential. And then I say, oh, well, that's interesting because look, exactly what I have here is exactly what I've got there. And this guy is what I called u. So this is really just du over u, which we've dealt with before. It's the natural log of u. And then what was u? It was secant x plus tangent of x plus c. So this sort of evilly chosen thing to multiply by, oops, sorry, let me scroll up a little bit. Um, this sort of cleverly chosen thing to multiply by turns out to do exactly what we wanted. Um, and again, you know, maybe you wouldn't have come up with that on your own unless I locked you in a room or something and said you can't come out until you figure it out. Um, so anyway, now similarly, if we can do this for secant, we can do it for cosecant. But here, here the magic term to multiply by, and I'll let you guys work this out as sort of exercise, you want to use cosecant of x minus cotangent of x. Okay, so so let me give you a couple of exercises to do for Wednesday, and then we'll talk about them first thing Wednesday in class. So we did the integral of tangent. So you guys do the integral of cotangent, and we did the integral of secant. So you guys do the integral of cosecant. So they'll go similar to how these two did for us. Not quite identical, but yeah, those will be some good practice. Yeah, so please take a stab at those for Wednesday, and we'll talk about those things first thing. Just remind me first thing Wednesday to talk about those because I'm liable to forget. Um, okay. Um, so the next thing I want to do is look at sort of some clever other situations um, where you have to be a little bit sneaky with the substitution technique, and uh, what I'll call these are sort of flip-flop substitutions, but we'll see what that looks like. Okay, so let's take as another example this. Okay, so we really only have one option here, and that's letting u equals x plus 3. Um, and I'll give you guys a hint. Um, if all you do is let u equal x, all that's going to do is change the letters from x to u. It won't actually change the integral that you've got. So that's not going to be the trick that you want to use. Um, okay. So in this case, we really have only one other option, which is letting u equals x plus 3. Well, if we do that, then du is just 1 dx because the derivative of x is 1. And so we might say, all right, well, this will give me the integral of x square root of u du, because du and dx are the same thing. And we might say, wait a minute, Dr. C, now we're stuck, right? You told us that whenever you get to this point and not all the x's go away, then you've probably messed up. And in general, that's a good kind of rule of thumb. But in this particular case, we can do something kind of clever, which is here we have u equals x plus 3. So if u equals x plus 3, what's x? Yeah, it's just u minus 3. Okay, and then we can substitute that in here. And so I'd have u minus 3 times root u du, which I'm going to rewrite as u to the 1/2, which will become a useful way to write it in a moment. Um, Okay, so this is why I like to call these sort of flippy flop substitutions. I mean, it's a U substitution, but what we did was we actually solved the U equation, which was started as U as a function of X, and we flipped it and solved it for X as a function of U. Um, and in this case, right, it was a very obvious or easy relationship. They were sort of linearly related. Um, and um, in Calc 2, you'll look at sort of other examples where this is a little bit more complicated, but anyway. All right, so now that I've got that, what I can go ahead and do is distribute everything. And then, of course, u times u to the half would be u to the 3 halves, and u to the half is just u to the half, but with the 3 out front because of the u minus 3 term. Okay, so now that I've got it there, I can just do the power rule. So this would be 2/5 u to the 5 halves minus 3 times u to the 3 halves times 2/3 plus c. And then the 3's happen to cancel here. And so we get 2/5, well, u to the 5 halves minus 2 u to the 3 halves. Okay, and then what was u? Well, it was x plus 3, so I just replaced that with what we had to get going. Okay, so the sneaky trick here, right, was to this part to realize that if u is a function of x, then um, if u is a sort of simple function of x, then perhaps we could rewrite that as x being a function of u. Um, and why that's justified, well, it depends on the function of x that you've got. So in this case, we had a linear function, and so that meant that we could solve the other direction without any trouble. Where you would not be able to do this necessarily is if you had square roots or other functions that were maybe a little bit um, uh, well, that weren't one-to-one functions, basically. Um, okay, so let's look at another example of where this sort of trick is a good idea, and that's something like this. Okay, so if this fraction were x plus 1 over x, we could break it up into two pieces and integrate, and that would be the end of it. But it's not. The sum is in the denominator, and so we can't break this fraction up any. All right, so let's try what we did before. And then we can say, oh, well, this is u minus 1 over u du. Okay, so what this does is it basically takes the problem that we had, which was a sum in the denominator, and converts it into being a sum, or in this case a difference because of the minus, in the numerator. And that's good because now we can break up the fraction like that, right? So u over u is 1, and 1 over u is, well, 1 over u with a minus sign in front, of course. And now it's easy because the integral of 1 is just u, and the integral of 1 over u is the natural log of u, and then, of course, our plus c. And then all we have to do is replace our u with what it was. So we had x plus 1 minus natural log of x plus 1 plus c, which, let me just write this one other way, and let's think about why this is equivalent. Um, so if I had put this, for example, into Mathematica, I might have gotten the second answer down there at the bottom instead of the first one. Are those two things the same? I mean, I claim that they're the same thing. Why are they the same thing? Yeah, good question. So it looks like the plus one just sort of just magically disappeared. And yeah, Matt, that's exactly it, right? So plus one plus some random constant that we don't know what it is just some other random constant that we don't know, right? So I can sweep that plus one to be part of the plus c and just write it in the second form there at the end. And this all comes down to the fact that we don't have any clue what plus c is, right? It's some arbitrary constant. And yeah. So so that's worth pointing out that if you guys plug some of these things into either Mathematica or Wolfram Alpha or you have a TI-89 or something fancy like that, um, then you have to be a little bit careful because you might get an answer that looks different than what you have, but it could be the case that it's correct. Um, Okay, so just be a little careful with that. Um, okay, so we've done some trig functions, um, and let's um, let's look at let's see, let's look at some more examples here. All right, so let me go over to a clean sheet here, and let's say that we had a situation like this. All right, so any brilliant ideas here? And in fact, as a hint, okay, so you can't really factor that one because it's a sum of two squares, not a difference of two squares. So that's not going to work. But dx over x squared plus 1, or 1 plus x squared, same thing. Does that remind you guys of anything? Does that integral on the right, antiderivative of 1 over x squared plus 1, does that ring a bell at all? Ding ding. Not quite. Well, that's unfortunate because it's our dear friend arctangent. Okay. So let's remind ourselves. Do we remember this now? I'm judging by the long string of O's followed by an H that Willie, this is ringing a bell now. What about the rest of you? Rest of you gentlemen. And again, kind of an impressive that even including Dr. Dunaway, we've got more people in the stream here than are in the class. So this is sort of the opposite of the problem I have in computer science, where I've got like half of the people that are in class every day. All right, so why was it 1 over 1 plus x squared was the derivative of arctangent? Do we remember why we got that, how we got that? All right, so let's go back through it actually, because it's been maybe a little while. So if let me say that y equals arctan of x. Well, this means that x equals tangent of y, and y is between negative pi halves and pi halves. All right, well, if I've got an equation here, I can differentiate this implicitly. Okay, so let me actually write here. Can use implicit differentiation, right? And say, all right, well, if x is tangent y, then the derivative of the left equals the derivative of the right. The derivative of the left is just 1, and the derivative of the right is secant squared y times dy dx, because y depends on x. So solve this for dy dx, and it would be 1 over secant squared, which is the same thing as cosine squared. And then I say, okay, well, I'm going to consider a right triangle where x is the tangent of y. And in my diagram, if I put an x on the opposite and a 1 on the adjacent, well, what is tangent of an angle? It's opposite over adjacent. Okay, so if I put the x on the opposite and the 1 on the adjacent, then tangent of y is x over 1, or just x. That makes the hypotenuse square root of 1 plus x squared by Pythagoras' theorem. And then I come over here and say, all right, well, what's cos squared? Well, it's whatever cosine is, squared. What's cosine? It's the opposite, or sorry, adjacent, over the hypotenuse. And then the square and the square root kill each other. And we're just left with 1 plus x squared in the denominator. Okay, so yeah, so our dear friends, the inverse trig functions, are still on the table. So let's go back to the original problem at hand and see what we can do. All right, so we had that. Now, if this had just been 1 plus x squared in the denominator, then we would have been set, right? Because we could have just, well, it would just be arctangent, and that would have been the end of it. But it's not. We got this pesky 25 there. So what I'm going to do is I'm going to say, all right, I'm going to factor this out. But if I do that, then the coefficient of the x squared is now 1/25, right? Because it started as a 1 and I pulled a 25 out of it. And if you're ever not sure, well, multiply out what you got, and if we get back to where we started, then we've done it right. Okay, so now that we've got that, um, the next thing I'm going to do is a little sneaky. Um, and basically, I want to set myself up to having something of the form 1 plus something squared. So I can think of that x squared over 25 as really being x squared over 5 squared, or another way of saying that would be x over 5 whole thing squared. Right? So I basically took the 25 and buddied him up with the x squared, and then sort of factored it. Okay, now that I've done that, I have something that looks kind of like what I want. It's 1 plus something squared. So let's try letting u equal to the something. Okay, and if u is x over 5, then its derivative, or differential rather, is dx over 5. So dx in this case would be 5 du. All right, so dx we said was 5 du. Then we have 25, 1 plus u squared. All right, 5 over 25 is 1/5, which, because it's a constant, I can pull out of the integral. And now I have, oops, I'm sorry, I need to scroll up a little bit for you guys. Now I just have du over 1 plus u squared, which was arctan of u, like we said earlier. Okay, so if the derivative of arctan is 1 over 1 plus u squared, then the antiderivative of 1 over 1 plus u squared is arctan. And then what do we just need to do to finish? Well, what was u? It was x over 5. So this would be 1/5 arctan of x over 5 plus c. Okay. Um, so hopefully that clears out a few cobwebs in terms of uh, the uh, the inverse trig functions. It's probably been a little while since we've talked about those. Um, you can do this sort of thing with arc sine and arc cosine, which um, which is, great and all. Um, but yeah. Um, okay. So, any questions so far? Hopefully that kind of makes sense. All right. Well, let's go on to a clean sheet here then. Um, all right. So what we've talked about so far are indefinite integrals, meaning um, they didn't involve numbers at all for the bounds. And so the question now is, what would we do if we had a problem where there were bounds on the integral? So let's just take as by way of example, say we had this. So we, with this U-substitution technique, can figure out the indefinite integral. And then we could plug back in our answers at the end. Okay, so there's two methods to do this. So method one is just pretend that the problem is like what we had before. There were no numbers, and just let's do the antiderivative that way. Okay, so let's start here. And in this case, we want to do a u substitution. I choose to do u equals sine. And so the integral is just u du in this case, which is very easy. It's just that. So once I've got the antiderivative, then I could say, oh, well, then if I have a definite integral, it'll just be the antiderivative, and then I just have to plug in my numbers. Okay, and so then I'd say, all right, well, this is sine squared 1/2 sine squared of pi halves minus 1/2 sine squared of 0. And then, well, what's sine of pi halves, gentlemen? You're lucky we're not all on campus, because that means I can't give you guys a punishment quiz and for your unit circles. So sine of pi halves is don't make Dr. Dunaway save your bacon again. Yeah, it's 1. So you square it, you get 1, and then we have a half out front, so it's just a half. And then what about sine of 0, Willie? So what's sine of 0? What am I going to put inside the parentheses there? Yeah, it's 0. Okay, so we just get a half in the end. Okay, so that's method 1, right? Method 1 is just pretend that the problem that you had didn't have any numbers at all. Figure out the antiderivative, just like we did before, and then plug in the numbers to it. Okay, that perfectly works well. And oftentimes when I'm working one of these, that's actually the approach I take. Um, because it means that I can concentrate on one thing at a time. I can concentrate on the integration and then worry about the number crunching. Um, but there is a second technique, and I'll point it out because it's useful in some other contexts. Okay, so the other technique is to concentrate on the numbers and what you made u. Because if x is 0, then u would be sine of 0, which is 0. And if x is pi halves, then u equals sine of pi halves, which is 1. Okay, so what I've done there is I've taken the bounds of my problem, okay, and these bounds are in terms of x because it's blah, blah, blah dx. Okay, so the integral is in terms of x, and that tells me that the 0 and the pi halves that are written there are x numbers. Okay, and so if we then say u equals sine of x, and we have values of x, if I plug those in, then I get two values of u. And in this case, I get, for the bottom one, when x is 0, I get 0, because sine of 0 is 0. And when um, x is pi halves, then I get sine of pi halves, which is 1. And so what happens, is I get now the same integral that we had before, but now it has a 0 and a 1. And those came from here. Okay, so uh, now yes, 0 and 1 are different than 0 and pi halves, but the reason that I've got 0 and 1 here is because I took the two x bounds, the numbers that are circled in orange there, I plugged them into my formula for u in terms of x, and I got 0 and 1 out. Okay, so this is sort of converting the bounds from one variable to the other. And now that I've done that, I can just say, oh, well, the antiderivative of u is u squared over 2. Okay, that's easy. Um, and then I just have to plug in 1 and 0, and so I get a half minus 0, which is a half, and that's the end of it. Okay, so either method is acceptable. I mean, they both work. Um, but sort of the benefits of one versus the other. The first one, I think, is nice because you are only doing one thing at a time. You're first worrying about the integral and then worrying about all the number crunching. But um, the second version is maybe especially nice, and for those of you who go on to maybe either situations in econ or certainly in math or physics, then switching the bounds and thinking of it in a different way, like we did here, is kind of is also handy. Um, right. Okay, so just kind of to recap here, um, we mostly spent today talking about U-substitutions as a method of doing indefinite integrals, and then at the very end we said, okay, how can we do this with definite integrals? And for the most part, it's not a whole giant change. So all right. Well, let's. Just by way of reminder, take a look at those two sort of quick exercises: the integral of cosecant and the integral of cotangent, and see if you guys can figure those out for Wednesday. We'll start with that thing first thing Wednesday. Maybe work a few more examples of this, and then I think probably the rest of the day Wednesday. So after we do just a little bit more of this U-substitution stuff, then we're basically done with material. Um, so um, in the second sort of half of class Wednesday and definitely on Friday, basically we'll just make question and answer um, day. So have a peek at the Infinity exercises. I know a bunch of you guys you've gotten started on them, and maybe you're running into ones where you've got some questions. So I'd like to handle that on second half of Wednesday and then also on Friday. All right, so we'll quit the stream here, and I will see you guys on Wednesday, if not sooner. Have a good rest of your day.